Good morning, guys. This is Professor Mane. We will start our next unit, two-dimensional elements. Okay. So in this unit, we will see actually the syllabus for this two-dimensional elements is what two-dimensional stress analysis, in which we will see plane stress, plane strain problems, or plane stress, plane strain conditions in two-dimensional elasticity. Then next we will see the constitutive relationships for this plane stress and plane strain conditions. Then we will see the constant strain triangle, means CST element. What are the CST element? What are the types of CST element? Then we will see the linear strain rectangle, LSR. Okay, so we will see what are these LSR elements, or what are the types of these LSR elements, how to apply these LSR elements in your hypermesh or in your ANSYS. Then we will see the different types of displacement functions, means what are the displacement functions? Polynomial shape functions are there, means one-dimensional, two-dimensional, three-dimensional, means your linear, hyperbolic, parabolic, cubic. These are the types of your displacement functions. We will see in we will see these displacement functions in detail. Then what are the convergence criteria for element? For this we will see the Pascal's triangle. Then we will see the compatibility and completeness requirement. In that we will see the geometric isotropy. What is the geometric isotropy? What is the need of this geometric isotropy? And then finally we will see the strain and stress field for this two-dimensional element. Okay, so we will see one by one. So first we need to distinguish between one-dimensional, two-dimensional and three-dimensional elements. Okay, so as we know that one-dimensional elements, it means only one dimension is measurable as compared to other two dimensions. Means for example, a shaft, here only length is measurable as compared to your thickness and width. Then for two-dimensional elements, you know that two dimensions are comparable. Okay, so in this case, thickness, we can neglect this thickness parameter, and we can take breadth and width as a measurable parameters for this two-dimensional geometry. Okay, so this is your two-dimensional element or two-dimensional geometry. And in three-dimensional problem, we can measure 3 dimensions of that element. Okay, so 3 dimensions are comparable or measurable. Okay, so this is the main main difference between one-dimensional, two-dimensional and three-dimensional elements. So in one-dimensional element, as we know that only length is the parameter which is measurable or comparable as compared to your second and third parameter. And for your second two-dimensional element, there are 2 parameters, as we know that if we consider a thin plate or a thin disc. Okay, so in this case, this thickness it is very less as compared to your other 2 dimensions. Okay, so we can neglect, or the thickness is negligible as compared to other 2 dimensions, so we can neglect this thickness dimensions. So this problem will become a case of your two-dimensional element or two-dimensional problem. And three-dimensional problem, as we have studied or discussed these things in your previous lecture, that for three-dimensional problem, if we consider a duster, okay, actually we know that this duster has 3 comparable parameters or 3 comparable dimensions, means your length, width and breadth, these are comparable to each other. So this is your three-dimensional geometry. Okay, so we will see the basic difference based on the actual model, finite element expression and your additional requirement. Okay, so first we will distinguish these first one-dimensional, two-dimensional and three-dimensional elements based on your actual models. Okay, so for example, actual models, it will consist a rod or truss problem, okay, or your beam problem. This is considered to be a one-dimensional problem. Okay, then for two-dimensional problem, for examples are shell, plane stress or plane strain, or thick plate or thin plate, or you can say your disc, thin disc. These problems or these examples are considered to be your two-dimensional problems. Okay, and for three-dimensional problems, all solid elements or solid geometries are considered to be your three-dimensional problems. For example, your duster, a ball, it is also considered to be a three-dimensional geometry. Okay, So solid elements or solid geometries are considered to be a three-dimensional elements or three-dimensional problems based on these actual models. Now second, we will distinguish these three elements based on your finite element presentation or finite element expressions. Okay, so finite element expressions means what? We will distinguish these three elements or three geometries, one dimensional, two dimensional and three dimensional, based on the geometric properties which are defined by the nodes. Okay, so as we know that for one dimensional element there are only two nodes, there must be only two nodes. Okay, for one as we have studied for during your bar element, your shaft element or your truss element, we have considered only two elements to define this geometry. So we need to, if we need to define the one dimensional geometry, so we need only two nodes. Okay, so by using these two nodes you can compare or you can measure the one parameter only. It is nothing but your length. So for finite element expressions we need a length for that element, or if the one dimensional geometry is there, then we need length as a measurable or geometric property for that element. Then next is what? For two dimensional element. So for two dimensional element, to define the two dimensional element we need minimum three nodes. Okay, so to define the two dimensional element in your finite elemental expression we need minimum three nodes. Okay, so your triangle, so minimum three nodes, it means what? We need to express this element in as a area. Okay, minimum three elements means by joining this we can get area of that shape. Okay, so it may be triangular. If we consider a four noded element, then it may be it will become a quadrilateral or a rectangle or a square. Okay, so here area is the geometric property to define the two dimensional element. Okay, as we know that minimum three nodes are required. So by using these three nodes, area, we can measure the area by using these three nodes. So area is the major property while considering for two dimensional element. Now next one is what? Third, three dimensional element. So for three dimensional element we need volume. As we know that the actual model is a type of solid. So to define the solid in finite elemental expression we need the volume of that element. Okay, so one dimensional element, the geometric properties defined in your finite elemental expression for one dimensional element is length, for two dimensional element is area, for three dimensional element it is volume. Okay, so in this way we can distinguish these three elements based on the geometric properties for your finite elemental expression. Now next is what?